Alright, so where is it? Alright. So I've started the recording. Welcome back. We will be moving on to another aspect of our choppers, and we're going to be looking at primarily how we classify them. Right? They are normally classified depending on the input and the output voltage levels. So you can say they are step up or step down. Right? That's the main way we classify them. Also, according to the direction in which we have the output voltage and the current, right? We can have what we call a class A chopper. We can have a class B, a class C chopper, right? In a little while, you'll see that the class C chopper is just a combination of your class A and your class B type chopper, right? There's also the class D chopper and the class E chopper. For the purposes of this course, we will study only the first three, right? So class A, class B, and class C type chopper. All right, so I will show you a diagram here just to let you have some kind of appreciation as to the whole classification method. Right? You recall when I told you earlier on that we can classify according to direction in which we have the output voltage and current, right? Also according to input output voltage, of step up or step down, right? Is it step up? Is it step down type chopper, right? The class A, right? So depending on the output voltage, current, and direction. So let's look at this IV curve. Right, so for your class A, it is such that you have your positive current and a positive voltage, right? So that is what is reflected in the first diagram here, A. When we look at class B, right, we have a positive output voltage, right? This is the output voltage and the output current, right? Positive output voltage, and we have a negative output current. So that's a class B type chopper, right? When we look at the class C, I told you earlier on, it's just a combination of A and B, as you can see here, right? So we have positive voltage, output voltage that is. However, we have negative and positive output current, right? So that's our class C type chopper. Class E, right? You're seeing a positive current. However, we can have a positive and negative output voltage. And with your class E type chopper, right, what you're seeing, you have both positive and negative output voltage and both negative and positive output current. All right, so it's the first three that we'll study, class A, B, and C type chopper. Right, so you're probably wondering what kind of applications we can have for this. Then you can use it in motor control when you're doing machines. I think too, you'd probably have been exposed to this to some degree. just refresh your memory. Those of you who perhaps for whatever reason I was not exposed to it. All right, so we can basically control the speed, the motor, and also for braking. All right, so if we look at this diagram, we have different quadrants, quadrant 1, 2, 3, and 4. Right, so if we operate the motor in the first quadrant where we have a positive speed and apply a positive torque, that's when we have what your forward motoring. Right, we can have reverse motoring, however, if we apply a negative torque and a negative speed. That's the reverse motoring. Right, now for forward braking, we have that positive speed, however, we now make the torque negative. We have a forward braking of the motor. Right, we can have reverse braking, where we would operate in the fourth quadrant, right, where we now apply have that positive torque, however, the speed has been reversed. So we have reverse braking, right? So these are a typical, what we call a four quadrant chopper. All right, so we'll start our study with the class A. I don't know why it's like, oh, okay, all right. All right, so a class A chopper. Okay, so we have a DC input, we have a chopper here. This could be a SCR that we have here, and as you can see here, this is a freewheeling diode, and we have our load. All right, here our load could be our motor, and in that case could be some kind of inductive load that we have there. All right, so I want you to look at the diagram for a brief moment and try to analyze it, right? That is the current and the voltage, the output voltage and current positive, right? Are they positive, right? Because that must be the condition for it to be a class A chopper. So I wanted to look at it for a few minutes, and then you can tell me what is happening, right? Somebody to volunteer and explain to me when the chopper is on, what is happening, when the chopper is off, what is happening. Right, I'll just give you a few minutes, right? So this chopper turns on, so it turns on meaning that maybe the gate is a narrow positive pulse that has been applied at the gate, but we're not getting to that part. You know how to turn on these devices now. Right, so when this chopper is on, what is happening? When the chopper is off, what is happening? Right, I want somebody to tell me. This is a simple case.
Sir.
Yes.
Imagine the load is a resistor, sir. So imagining. So
let us say it is some kind of inductive load, because remember that's for practical purposes. This is where again apply. Let us say it's a inductive load, so it would have some amount of resistance and some amount of inductance, but it's not a pure inductor.
okay.
Yes. All right. So what is that? You know,
when you fire the whichever fire driver circuit and the current begins to flow, then it
right?
would
So,
go into the load. So you'd have that would be a positive current going to the right into the load.
okay.
Yes. Would be positive at the top there, and the current would be also positive.
Mm-hmm.
And the fluid, the diode, there will be no current flow into the diode because it will be reverse bias. But
All right. That's when the chopper is turned on. All right. Good. All right.
when you turn off the chopper now, if since it's an inductive load, you're going to have the what's that now? The current flow in the opposite direction.
Current flow in the opposite direction.
The inductor is going to resist the change. The current will do the freewheeling diode, sir.
Right. Go through the freewheeling diagram. So basically, the current would maintain in the same direction.
Yes, sir.
Mm-hmm.
So it's always positive.
Right. So either way, it is all, and we have a positive voltage. Right. So that's very good. Very good. Very good. And all right. So as you can say, which direction we're going from?
From the left
So
to
it's
right.
going from the source to the load. So we can use this to control basically the speed of your DC motor. All right. That's a very good, Conrad. Very good. All right. So everybody understood? All right. So basically, what he's saying that when this chopper turns on, all right, you would have um, voltage across the load, positive voltage across the load. You would have no current. The current that would flow at that time, none would go through this diode here. Right? So instead, the current would be in this direction. All right. However, when the chopper turns off, um, of course, know what you have, because this load could be a motor here and it's inductive in nature. You would have no that energy that would have been stored in the inductor being dissipated. So we have a current now that will now flow through this freewheeling diode. So it maintains that path that the current was flowing initially. So again, the current is positive, the voltage is positive, right? So whether chopper is on or off, we are seeing a positive output current and a positive output voltage. So hence we have this kind of IV curve, right? So we know that this behavior is typical of a class A chopper. And as we say, we can use this to control the speed of our DC motor, right? This is typically a step down, right? So this would be a step down chopper, right? Because we have the power that's flowing from the source to the load here. All right, so very good, very good. All right,
So, quick question. The copper is off. There would be energy stored in the inductive load, right?
yeah,
Is it um always there or run out at some point?
if it is all well, after some, it will dissipate, and then the chopper will switch back on.
Okay.
Right, so you will have some amount of energy there. So I guess depending on the timing of this chopper, or, you know, then you'll have um the energy stored being dissipated at that rate.
Okay, sir.
All right. All right. So it's basically what we said here that documented. So we can look at the graph. All right. So this could be the pulse that we apply at the gate. You can see here. All right. So when we apply that pulse, what we are getting, what is going to happen? The output voltage, right? When we turn that chopper, which in this case would be some thyristor, we get output voltage, right? So this is what is shown here, that output voltage. And of course, the current would flow, right? Of course, we have a gradual build-up of current in our load, right? Because it's inductive, right? And then what you're seeing when the chopper turns off, and we have that current energy that is stored in the inductor being dissipated, right? So the current now flowing through that freewheeling diode, right? So the chopper then turns on, right? Because the thyristor pulse now applied at the gate. So output voltage now is across the load, and again we have a current flowing through the load, right? So this is the behavior being summarized here in this graph. All right, so that was very simple and very good. It seems like most of you were able to understand it. All right, so we can move to the next circuit. Of course, I'm going to ask you to do the same thing. I look at it for a brief moment. This is class B. I'm telling you it's class B, and if it's class B, it must be such that the output voltage is going to be positive, and you're going to have a current in the opposite direction, right? So if you can analyze this circuit and see this kind of behavior, then it is good, right? So in this one, I basically draw the load out for you, what is happening. So this here would be the back EMF, right? That part, so that's why I put that battery there. That could be your back EMF there. All right, so I want you to analyze the circuit. Again, the same way, chopper turn on, what is happening? Chopper turns off, what is happening, right? Let's look at it for a brief moment. Any suggestions? No suggestion. Seems like this one is a bit difficult. All right. Let's analyze what is happening here. As you can see, when this chopper turns on, right, it's as if we have created a short circuit here. So this is on. So at that time, you will have current, right? So your EMF will be supplied from this source here, E, right? So the current is going to now be going in the opposite direction, right? So you have seen that in the first instance when the chopper is turned on, right? Also, when the chopper is turned on, the voltage that would be across your load here, right, is positive, right? So that is observed there. Now, when this chopper turns off, what is going to happen now? You're going to have the energy that is stored in the inductor being released, right? So, of course, the diode here would now be forward biased. Previously, it would have been reverse biased when the chopper was on, right? So your diode here would have been reverse biased, right? So chopper turns on, off, yes.
So it wouldn't depend on the value of V, like how big it is compared to bracket. Yeah.
The output voltage here,
Yes, sir.
for what happened?
For the V to be reverse or forward bias.
All right, but if you look at what is happening, the chopper is going to turn on, right? When this turns on, what you're basically doing, right? It's like a short circuit. So it doesn't matter if this is larger than the input. Right? So it will not cause any current to flow in this direction through the diode.
Yes, sir. I was talking about this off.
When it is off,
Yes,
right?
sir.
When this is off, then what you're going to have happening is the diode now becoming forward bias, right? It's now forward biased.
With respect to the energy in the load, sir.
Right. So the energy that is stored in the load is now going to be dissipated, and as you can see, the current will now flow in the opposite direction. So basically, you have the power flow now is such that you have it going back to the supply. Right. So part of the energy that you have stored in the inductor is returned to the supply. I don't know if you're following or how I'm answering your question. Is it making it clearer to you?
Yes, sir. It's a clear, but I'm saying relative the inductive supply, the inductive load, right? There would be a EMF going back to the diode to forward bias it, right? But there's also opposing current going to the cathode side of the diode to make it reverse bias. So I'm saying in order to the junction, the from the load should be higher than V, the current coming from the supply, in order to forward bias it.
Yeah. Right, right. You're right. So
Oh, yeah.
that's a good observation. So what kind of would you call this a step up or step down type?
Step up.
Right. That's very good. So it would be a step up, right? So that's what it is. So we also refer to this, the class B chopper, the step up chopper. So you're right.
Okay.
Yes, you're right. We refer to it as a step up chopper. Right, so that is what is happening when we switch when the chopper is off. We have some of the current now going back to the source, right? So we have power going back to the source, part of it going back to the source. However, as you can see, the voltage is always positive, right? So this qualifies for a class B chopper where you have a negative current, and in either case, when the chopper is turned on and off, right, our average current is negative. However, our voltage, output voltage, is always positive in either case. So we have here the condition for class B chopper. And as you have seen earlier on, this is a step up type chopper, and that's another name for the class B chopper, step up. But where could we use this? Right? Where could find use for this? Right? We could use it in electric vehicles, right? You'll find this, right? So this is what is electric vehicle now getting popular, right? Regenerative braking. I don't know if you have covered that in your machines too, right? The regenerative braking. This is what is happening, right? Would use this as a brake on your motor, right? So this is one of the advantages with the electric vehicle. So you don't have to change your brake pads often, right? Because you can use the regenerative braking in the vehicle. So you're basically reducing the maintenance costs of your electric vehicle, right? So it has application, right? And all right, so very good. You're able to identify some of the main points that I wanted to highlight, in particular this one. You're able to see that it is a step-up chopper, right? So remember that for this class of chopper, you can use it for braking and for DC motors, right? So we can find it in more electric vehicles. All right, so we can now look at the waveform, right? Normally, it should now summarize all of what we spoke about just now, right? So look here, we have our pulse, right? Pulse on, pulse off, right, at the gate of our thyristor, right, and we look at what is happening at the output, right? So when the pulse is, when we don't have any pulse, what's the output voltage, right? When there's no pulse applied, we realize that we have an output voltage, right? When we apply the pulse and the SCR turns on, you realize that our output voltage is 0. Right? If you look at the diagram, you'd have picked that up and just go back. Right? Right, so this chopper turns on. What is your output voltage? Sorry, not that, class B. Class B. Chopper turns on. What's your output voltage? Right, remember this is like an open circuit you have here. Sorry, a short circuit when this turns on. So the voltage across this would basically be 0, right? When the chopper turns off, that's when you have that maximum voltage here, right? So that's what you have happening as the output voltage. So it's always positive voltage you have. And of course, you would have seen where you have the diode conducting when the chopper was off, right? So we have E supplying a current, right? So the diode would have been conducting in the case when the chopper, sorry, this is when the chopper is turned off, right? Chopper turns off. You recall that the energy that is stored in the, let me go back so that you can see what I'm saying. When the chopper is turned off, you will recall, you can see clearly that you have had energy that is stored in the inductor that would now be released, and some of the power would now be going back to the source through this diode. So as I said, at that point when the chopper turns off, this diode now conducting. Right, so that's what I'm showing here. So here, thyristor off, diode is now conducting. Right, when we have the thyristor turning on, right, we have the chopper conducting, and it is at that point that the energy that is stored in the inductor is now being released, hence it gradually decreases here, right? So that's the summary in the graph here. Right, now the next
Sir, quick question.
yes.
Generative braking as you speak of, can this be applied to, for example, a wind turbine, or a hurricane season when you know the wind is high and it can cause damage to the wind turbine itself? Used to slow it down, or
Yes, you can incorporate this kind of electronics to apply a brake. Right. In fact, power electronics is highly used in the renewable energy.
okay,
So you can design one for that condition, if it gets too high, then you apply some brake to it, right? So yes, you can use it. All right, now I'm going to now go to the next chopper, the Class C type chopper. That one normally, for some reason, most students normally have problems understanding it. I'm going to see how well you are able to receive it. So basically doing the same thing. This is our Class C chopper, right? We have the diagram, the circuit diagram, the general schematic for any Class C type chopper. And for it to be qualified as Class C chopper, your output voltage should be positive, and you can have a positive current as well as a negative current, right? So you're basically operating in two quadrants, right? So again, I give you a brief moment to look at this circuit and do a bit of analysis before I go through it. So here now it's two choppers we have. Before you're looking at one chopper, right? And now we have two diodes, not one, right? So yes, I will appreciate it that this has some added level of complexity, but nothing difficult. Nothing difficult. Just analyze what is happening when chopper turn on and chopper turn off. And of course, we're supplying our inductive type load, because that is practically what you will be using this for. All right, anybody?
Yes, sir. I think
All right. Before you start. I'm going to ask a question. Can you turn on the two choppers at the same time?
Yes, sir. Why not?
All right. All right. Any opposition to that?
Hold on, sir.
I'm asking if you can turn the two choppers on at the same time.
No, sir.
Why? That's very good. It would be very interesting if you're able to give me the reason. You are correct.
Would it be the case
What's
that we
what?
have current going to the load from both directions, sir?
No, that's wrong. Why you said no?
Sir, guys, when you close both of the or turn on both of the choppers, you'll be creating short circuits. So you will be basically blocking out, not sending any current to the load.
All right, very good, Matthew. You create
Yes.
a short circuit, right? If you turn on the two choppers at the same time, it's a short circuit. Oh, sorry. Why this jumping up and down? What you have here is a short circuit, right? Turn the two of them on at the same time, short circuit. You don't want that. So these two choppers should never be turned on at the same time. So when one chopper is on, the other one must be off, right? So chopper one turns on, chopper one must be off. Chopper two is on, chopper two must be off, right? So you must have them working with that kind of harmony there, right? So I think you're ready to start, Matthew.
Yes, sir. I can.
All right, go ahead. Let me hear.
So when chopper one is on, it can create a short circuit. So diode one will be out of the picture, and it flows. And there would be an open circuit at chopper two, so the direction will go right to the load and back, thus creating a positive current and voltage. And when chopper two is on and chopper one is closed, is out, sorry. You can see the E would be providing the current back to chopper two, so it will be flowing to the left back to. So therefore, you will get a negative current.
Yes, yes. Very good, very good, very good. So where you think we could apply this kind of a circuit?
Like for example, assembly line,
And where?
conveyor belt or something. So
All right. So what would you be doing?
so basically, you have a forward button and a reverse button.
All right, all right, all right. Good. You can use it there. So you basically have motor control and regenerative braking of the motor, the DC motor. All right. What kind of chopper you say this? Step up, step down, or both?
Would be both.
Yeah.
It's both.
Yes. That's very good. That's very good. Very good, Matthew. In class, you follow what Matthew was saying a while ago?
Yes, sir.
All right, that's very good. Good, very good, Matthew. So, basically, for the first quadrant operation, you would have chopper one being on, right? Or we could say diode two conduct, right? Either way, right? So, for the second quadrant operation, we say the chopper one, the chopper two will be on, right? Chopper two will be on, or we can make diode one conduct, right? However, when we have chopper one on, we'll have the load current becoming positive, right? Chopper one on, our load current become positive, right? As you can see here. All right, so the output voltage at this time will just be equal to V, right? Right there. And the load will just receive the power from the source, right? So this is typical of the 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 the, the, the class A chopper that we look at earlier on, right? So this is a step down chopper type chopper, right? When chopper one is now turned off, when this is turned off, what is going to happen? The energy that we have stored in the inductor is going to force the current now to flow through diode to diode 2, right? Going to flow because you now have the energy being released, so that will now flow through diode 2. All right, so at that point, the output voltage is going to be equal to 0, right? Because this diode would now be on. Right? So your output voltage now goes to 0. Once this diode turns on, output voltage will now go to 0, right? So the current will flow now in the positive direction when chopper 2 is triggered, and the voltage here E forces current now to flow in the opposite direction through L, right? At that point now your output voltage goes to 0. Right? So when we turn off chopper 2, energy that we have stored in diode in the inductance drives current through diode 1, right? So output voltage is going to be V, right? So it's positive, but the current is now negative because it now flow in the opposite direction, right? And so power is basically flowing from the load to the source, right? So basically the average output voltage is positive, right? And the average output current, as you can see here, can take on both values of being negative and positive, right? So That's very good, Matthew. Very good. Not many students are able to analyze the circuit the way you did. And of course, we, as I've said, we can find use for this for regenerative braking and for control of the motor. That can either be step up or step down. All right, so can look at the graph here, summarize the whole operation that is taking place. Right, so as we can see here, we have the pulses at the gate. You can see we ensure that we offset these pulses just to prevent two choppers from coming on at the same time. So the top graph is showing you the pulse that is applied to chopper 1, and the one immediately below it, that's the pulse that we have applied to chopper 2. All right, so at no time you're seeing the two choppers coming on at the same time. Chopper 1 is on, chopper 2 off. Chopper 1 is off, then we have chopper 1 coming on in this period. Right, so when we analyze, we have diode 1 conducting, as you'll recall, when chopper 1 was turned on. Okay, so that's why we have this in current, and of course the voltage was positive. And of course, when chopper 1 turns on, we have the current still been increasing. So it is when we have diode 1 and chopper 1 being turned on is when we had that current that would be flowing, right? So in this region, that's when we have our output voltage being positive. However, when we have chopper 2 coming on and diode 2 coming on, then we have the energy stored in the inductor being released, right? So that's why we have this gradual decrease in current. And at that time, we have an output voltage of 0 because the diode 2 comes on and it is right across the load. Right, and the analysis is similar as we continue with D1 and chopper 1 comes on and chopper 2. Right, so that basically provides the summary. All right, so we can move on to look at, I would have mentioned it earlier on in the course, the opto-isolators, but we will just look at it in a little slightly more details, right? So opto, right? We're talking about light. When we look at the prefix, isolators, right? So we're going to be isolating something with light, right? So let's look at it. So these are the common isolators that you will come across. Right, we have the infrared type, right, with our phototransistor, and we have type here with our Darlington pair. This is when we want to have higher drive current. And for this one, we could have a light activated SCR. That says we use larger loads. Right, we switch in larger loads, we can use this type. Or we have the triac output type here, light activated triac, right? Or we could actually put the triacs in this configuration. Of course, this is all packaged for you, right? So we have the infrared triac high current type configuration here. As I can see, in all cases of the opto-isolators, we're going to have a light, right? So when this when we apply some power to this side of our opto-isolator, right, then we have our light coming from this let's call it emitting diode, light emitting diode here, shines onto the base of this transistor and will cause it to turn on. So if you have another circuit that's connected at the output, right, this could be at some higher voltage, right? So you're basically using a small voltage to switch on much larger loads, right? And depending on the kind of load you may need for a higher current rating, so you can go for different configuration, your Darlington type output, your SCR type output, your triac type output, and so on, right? So depending on the application, you can select the most suitable SCR for your application. All right, so as I can see here, the isolation is light. We don't have any physical connection taking place inside the device. So another advantage with this device when compared to let's say the mechanical relay is that this is more reliable, right? For a mechanical relay, it can fail because it has the moving parts, and compared to your opto-isolator, we don't have any moving parts, right? It's all semiconductor based. All right, so you can look at this circuit. So here, this part is our opto-isolator, right? This is our drive, right? So this will form our drive circuit for this switch. I think somebody asked earlier on when we look at the power supply, the linear and the switch mode power supply. That's about the base drive. Right, so this is a typical example of that base drive circuitry that you could have applied. I don't know, maybe you have some of you doing projects. You will find this kind of circuitry to be useful, in particular when you're using your microcontroller. I know most projects seem to incorporate the use of microcontroller. So here you could have a signal coming from your microcontroller and you connect this directly to your opto-isolator that you have selected, right? So here you can see you have your light emitting diode. Maybe you get typically about 5 volts from your microcontroller. You would need to include some kind of limiting resistor so as to protect the light emitting diode here, right? So you can use the specification that is given on your opto-isolator. Okay, your input current should be so much. So what resistor would you select? Right, you're getting 5 volts, let's say, from your microcontroller's output, right? You don't want the current flowing through your LED to exceed the rating provided by the manufacturer. You're also told what the voltage drop across this LED should be, right? So let's say typically, let's say you want a 0.7 volts drop across this LED, and this is 5 volts, then you can easily work out the value resistor that you need to put in series here so as to protect the LED. All right, now let us move on. What's going to happen? So you receive this signal from your microcontroller, let us say. It activates your LED, your light shining onto this phototransistor. I want somebody to tell me what is going to be happening here. Right now that we have light shining onto this transistor, we have an intermediate circuitry set up here. We have 12 volts, we have a diode here, and we have a resistor at the collector of this transistor Q, so BJT, and we have our MOSFET here. What is happening? So we have 12 volts here, right? So light shines onto this. What's happening? The transistor is going to turn on, and what else? Any volunteer? This transistor turns on, and what happens?
So you have a current flowing.
The current flows from where?
You have a 12 volt source and
Yeah.
the transistor.
Okay, good. All right. So it flows through the phototransistor. And at that point, what is going to happen?
So you set as Q there'll be an output.
So will this transistor Q come on or off?
You will go on.
All right. So when this is, let's say this is on, so will this be able to turn this MOSFET on?
When the opto isolator comes on, sir, it should be enough to turn on the MOSFET.
All right, all right. Let's say the opto isolator is off. What is happening? This is off. No light is shining onto this. What do you have?
You still have the 12-volt source. You still have
There
the
will
12-volt source.
a voltage drop across the base of this transistor Q.
So it is the 12 volt still present at the terminal, the base terminal for Q.
Right. What would be at Q?
The 12 volt source is still at the base terminal, right?
Yeah. Let me see here.
Mm.
Right. So what? Oh,
So it will be the flow through the collector for the opto isolator and go to ground.
this is when it is off.
And the opto isolator is off.
Yes.
So the 12 volts would not be enough to cause an output at Q.
Okay. All right. All right. So what is going to happen now? You have what? There a voltage there.
Yeah, you'd have voltage there, sir.
Yeah.
You have some amount of voltage there.
Yeah, but would it switch? Be able to switch the MOSFET on?
No, sir.
Okay. All right. Any other answer? I think somebody was saying something in the who is this? Let me see who was saying something here. 12 volts. Can somebody give a Garrett Brown? 12 volts through R and Q. Not sure when are you making reference to this? You want to turn on your mic, Garrett? Yeah.
This is when the light is shining on the transistor.
Yes.
I was making reference to that previously.
Okay. Okay. All right. So, yes, Conrad, your analysis of the circuit is quite appropriate. All right, so you can look at this example. Right, so we have our logic circuit, could be a microcontroller here. And we have a 5 ohm resistor and we have a transistor Q1 connected here. Then we have this connected to an opto isolator shown here. Your task is to find out what is the value EX, what is this output, right? So that is what you are being asked. So you have two logic levels, right? It could be 0 volts that we get out in one instance, and when it's 5 volts, right? So I want you to tell me, when we have 0 volts coming out from your microcontroller, right? What is the output voltage here, EX, right? When we have 5 volts, right? I want you to tell me what is the output voltage there. right? So that's basically the question, right? So the upright isolator is used to change the voltage level from the logic circuit to higher voltage level required by other circuit, right? So we have 0 volts and 5 volts, right? So we're using our transistor here as a gain of 200, or LED, right? So this LED, I told that it needs 5 volts, sorry, 1.5 volts at 10 ampere. So this is typically what the manufacturer will tell you, right? So you need 1.5 volts at 10 amperes for this LED to be turned on. So based on that, you can see why there's a 350 ohm resistor that is built into the optocoupler, right? So if you just do that math, right? So you have 5 volts, voltage drop 1.5 across this LED, right? So that would be you have just about 3.5 volts, and it's at 10 ampere, right? Remember earlier on, I mentioned to you that the manufacturer would let you know what the specification is as it relates to the voltage that is required to switch this LED on, right? So you can now know whether or not, based on the output voltage from your microcontroller, whether it's going to be sufficient to switch this opto isolator on, right? So in this case, we can work that out quickly, right? I can see 5 volts you're supplying coming out of your micro controller here, or you apply this 5 volts here. So is it sufficient? You can check, right? There's a 350 ohm resistor in there, right? So what is the current, right? So if we're to work out this current, it would be the difference in voltage, 5 volts, and you'd have a voltage drop of 1.5 volts here. And we can divide this by the resistance, right? The resistance there is what, 350 ohms, right? So what's the current? Let me work that out.
0.0.
0.0. So that's what, 10 milliamperes, right? So it basically meets the manufacturer's specification, right? So that's what I was pointing out to you. All right. So now let's go back to this question. What is the output when we have 5 volts here, when coming out of your logic circuit? You said this is 5 volts. What is this output here equal to? I want you to analyze this circuit. Right?
Sir.
So, yes.
10 milliamp that the to need to
Up
turn
to
it on
diode.
the sorry, isolator.
Mhm.
What is here?
Yeah, what code, right? So I wanted to look at it, analyze it. When we have 5 volts applied to the base of this transistor, is it going to cause it to switch on or off, right? Because it switches on, so you would have a path now for current to flow in this circuit, thereby turning on this LED, right? So the LED turns on, it shines light onto this base, and therefore switching it on. Right, this switch is on. So basically, you're basically analyzing this circuit when it is switched on, right? So that simple circuit goes here, 1 kilo ohm resistor, and now this gone to ground. So what's the voltage here with respect to ground when this switch is on?
Would it you have the one? Okay, so it would be the 50 volts minus the voltage drop across the 1K, across the 1 kilo ohm resistor, sir.
Right, this is a 1 kilo ohm resistor.
Right, so it would be the voltage at EX would be the 50 volts minus the voltage drop across the 1 kilo ohm. Would that be correct?
50 minus,
The voltage drop across the 1K.
right, what is the voltage drop across the 1K?
I never worked out. I never reached that far.
Alright, if you were to put, to just measure across this point where I have the 50 and the EX here, right? So basically, you're trying to find there the voltage across the 1K. What would it be?
50 volts.
Would be
50.
right. 50 when this switch is on. When this switch is on, right? Or when it is off.
When it is on.
It is on, sir.
Huh?
It is on.
Alright, you get 50 across this. Alright. So what can you tell me therefore? So how about when the switch turns off? When we have 0, so basically this off, no light shining onto the diode, so this transistor is off. You measure across here, what would be the voltage?
50, sir.
Alright, so now I want you to tell me when the switch is on, when the switch is off, it's going to be the output voltage at EX with respect to the ground.
Sir, based on how it is designed, there's always going to be 50 volts at EX, regardless of when it's on.
There's always going to be 50. Do you agree, Matthew?
Yeah.
Huh?
I was on that said that.
You said that regardless of whether it is on or off, there's all, remember, no, measuring with respect to ground, right? When this is on, right? So you measure from this point EX to ground, measuring across the switch. The switch turns on, what's the voltage?
0 volts.
Right, right. So it is when it is off that you get the 50 volts there, right?
Oh,
Right. So cut it when we apply 5 volts. Basically, so that we're able to turn on this photo transistor. So therefore, when we get 5 volts from our logic circuit, we have what? A 0, right? A 0, basically 0 volts at EX. However, when there is 0 volts coming from our logic circuit here, this no light shines onto this. So therefore, your voltage, your output voltage here will be 50 volts, right? 50 volts, right? So if this is off, right, so we should have 50 volts, no current flowing through this transistor. Do you see that? Conrad? Conrad? Matthew?
Yes, sir. Yes. Yeah, I'm trying to see it, sir.
Oh, you're still trying to see it. If when this is 50 volts, right? So if this point and this point 50 volts, there's no potential difference, right? So therefore, no current is going to be flowing through this transistor at that point when this is off. Is that making sense?
Yes, sir.
Right. However, when turns on, right? Let's say ideally there's no voltage drop here, so basically right here would be at zero potential, 0. So we have a current that will now flow through the resistor. All right, so that's how you can analyze it. All right, so here I just want to bring your attention to a concept when we talk about the current transfer ratio, right? There's another specification that you'll probably come across, like current transfer ratio, right? So that's basically the ratio of your output current to input current, right? So current transfer ratio, you're told here that it is 60% output current to input current is 60%, so that's at 0.6. Right, so based on what you're seeing here, what would be the input current, right? So look at this circuit, we have our input current. You need to find out what this is. You have this kind of circuit connected at the output of your opto isolator, 20 volts through a 1 kilo ohm load here. And of course, the current here is 10. We are told that this current is 10 milliamperes. So what is the input current based on what the manufacturer specified? Right, so how much current you must have supplied to the input to meet this condition?
Sir, if the output is 10 milliamp, then you would you'd have input being I/O divided by 0.6.
And what you get?
0.0166 or 67.
So that's what in milliamp.
16.67 milliamps.
All right. So you basically need to rearrange, right? So your input here is just equal to your output over 0.6, right? And when you do that substitution, says 16.67 milliamperes, right? So this is normally a specification on your opto-isolator, right? Current transfer ratio, right? Just the ratio of the output current to the input current. All right, now we're going to move on to, I think this is the last section, but you still have to come back next week, right, for the final lesson before we wrap up. All right, but let's see if we can finish. I thought we're going to finish. No, we're not going to finish this because I have another important part. So two things we'll have to do when we return. All right, so let's see. Let me just look at the loss. So now that you have studied the semiconductor devices, and you see that we can apply the MOSFET as a switch for fast switching applications, right? Because of this switching, you're going to have losses in this device. How do we calculate these losses? That's going to be the focus of this section of the lesson. The MOSFET loss, right? We can have our on-state loss. Remember at the beginning, I would have shown you a diagram of the switch, and the switch goes from on to off. The kind of losses that you can have associated with it. Right, so we can have on-state loss. That's what we call the conduction loss. That is given by this expression that we have here. Right, so just the square of your square of the current, the drain current, that is, multiplied by that drain source resistance, and of course multiplied by the duty cycle, right? So that's the ratio of your on time to the period, right? So you can have it rewritten in that way, where you have the square of your drain current multiplied by the square of the drain source resistance, right? You will get this from your data sheet multiplied by your duty cycle. right? So you could just use a duty cycle to get that information, right? The off state loss, you normally apply this formula for your off state, right? So your drain source, the maximum drain source voltage times the drain source current, and of course the ratio of off time to time there, right? So you can envision what is happening here. So off, right? So the time that is off, right? That ratio to the period, right? And you would get that fraction. You'd be able to capture that power, right? So power is voltage times the current, right? So you're basically capturing that amount of energy that could have been lost. All right. So it's energy that we have here. Energy, right? So remember, power joules per second, right? So if we multiply by time, we get in energy. So it's the energy that is lost here that we basically calculate in, right? So we can now look at the turn on switching loss for your MOSFET, right? And it's given by this expression. So we want to determine this turn on switching loss, right? So it's the drain source, the maximum voltage that drain current, and this TR, that's the rise time. Again, where you get this from? You get this information from the data sheet, right? You will check your data sheet for the MOSFET that you are using. Manufacturer will inform you of the rise time for that MOSFET, right? So you take the product of the drain source voltage and the current and the rise time, divide by 6, right? And by doing so, you'll be getting the turn on switching loss. To get the turn off, I guess you pick up what you'll be doing here. You use the fall time instead, right? So the turn off switching loss, right? So it's the same, except now you use the fall time. Again, this would be in the data sheet for the device that you have selected, right? Now, how about the power? Right, so what we're looking at here is basically the switching loss in terms of the energy. So how do we move from that energy to power, right? So the switching power loss, right, given by this expression here, right? So that energy that we have lost, turn on, and the energy loss turn off, multiply by the switching frequency here, right? So that's what we apply. And to get the total power that would be lost in a MOSFET, you basically taking the summation of all of those power that you would have calculated, right? So that's the general formula. All right, so let's look at an example before we actually finish. All right, so you have this circuit here, and you are given the parameters. You are told that the rise time is 2 microseconds, and the resistance between the drain and the source is 0.2 ohms when it comes on. And you are told that there's a duty cycle of 0.7 that is used at the gate, and the frequency is 30 kilohertz, right? So this duty cycle is as a result of that, let's say, pulse width modulation that you would have applied to that switch, as in the case of, let's say, the DC-DC converter, right? So you're asked to calculate power loss in the on state and the power loss during the turn on interval, right? I would have asked you to go through this, but in the interest of time, I will just provide you with the results. Right, so I'm looking at this. You recall we need to use the formula where we'll be able to get the energy at turn on, right? So how do we calculate that energy at turn on, right? It could be we need the to know what the drain current is going to be equal, right? What is going to be this drain to source current, right? How are we going to calculate it? When this comes on, we know that we have 100 volts across the device, right? We have this load of 12 ohms, right? So what's going to be the current, right? You can work that out. What is going to be the current there? No answer. Right, it's going to just be 100. Huh?
Voltage divided by the resistance.
The total
Right.
resistance.
Right. So 100
By
divided by
12.
so 12 plus 0.2, right? Because we have a drain source distance here. So when you take the 100 and you divide it by 12.2, what do you get here?
8.2.
Right, you get your 8.2. Is going to be your resistance, right? And you know what the current, what would be your current? What would be ID? Huh?
Repeat the question, sir.
What would be ID in current? What would be your drain current? That one should be simple.
RL plus
Right. You told me, right?
yeah, so it's RDS over RL plus RDS.
Right. So that gave you what, 8.2? That's what you said. Right. So so that's your drain current. All right, and so that's I square D multiplied by your resistance. That's what 0.2 when it turns on, and of course you can multiply that now by the time that it has been on for, right? The on time. So that will be the duty cycle multiplied by the period. That will give you the on time, right? Right. So you recall that the duty cycle is just the ratio of the on time to the period. So your E on is duty cycle times time, right? So that will give you the energy that is lost in the on state. All right. So to get the power loss, right? You then multiply by the frequency, right? All right. So you now have the basic idea. Just go through it here. All right. So we can get the period, right? But we know what the frequency is. That's give us 33.3 microsecond. Then to get the on time, I will calculate a while ago. I showed you. Just make the substitution. Your duty cycle is 0.7, and your period, we have calculated it here. So your T on, that's 23.3 microseconds. So now to get the energy loss, right? So that's I square, remember the power, that power loss, you multiply by the time that it has been on, will give us the energy, right? Because this part, power, joules per second, multiplied by time, will give us energy, right? So the energy loss during this time, we take the square, that's I square R, the square of the drain current multiplied by the drain source resistance when it is on. Of course, this value, we can get this, that's the resistance of the drain source. We get that from the manufacturer's data sheet. All right, so when we substitute our values, we get 313.74 microjoules. You can check on your calculator to ensure that these values are correct. However, if it's incorrect, the concept is correct. Right, so that's not a problem. Now, to get power, like I've said, we have our energy loss during that time when it is on. So to get the power, remember power is joules per second. So we need to multiply by the frequency, right? So that's a switching frequency, right? So it's turning on and on. So we have the energy loss, and we now need to know the rate of that loss. So that will give us the power. So by multiplying by that frequency, right, we're told that the frequency is 30 kilohertz. So you make that substitution, and if that's correct, we have here 9.4 watts. All right, that's pretty straightforward. All right, so the next part of the question, it asks you for the power loss during the turn on interval. Right, so the energy loss during the turn on, right, we can calculate it using the formula, right? Remember, I showed you a formula earlier on. So this is what, so the switching loss during turn on, so that maximum drain source voltage multiplied by this drain current divided by that rise time divided by 6. right? So that's what you are substituting here. So that maximum voltage is 100, the drain current was 8.2. You had calculated that earlier on, so you know how to get that. The rise time, that's a parameter that would have been supplied. We can get that from the manufacturer's data sheet. It's not given in the question. However, you have the data sheet, you could always get that value. Right? So you make all the appropriate substitution. You have 273.33 microjoules. Again, to get the power, we know the rate at which this switch is operating. That's the switching frequency. You just need to multiply by that. And here it is 30 kilohertz. Right, so you make that substitution, is 8.2 watts. Right, so very simple. These problems are not difficult. Just need to understand them and apply the formula. I think I have one. I'll give you one here for your homework. You can practice that one. Right, so you have to calculate the total power loss for the MOSFET, and the parameters are given there. You can try that one for your homework. So next week we will start another topic, the heat sinks. This topic is very important. Know that the transistor is switching at such high frequency. We may generate heat that may compromise the reliability of your device. So how can we keep it cool so as to keep it running how it is supposed to be running? So that will be the topic up for discussion when we meet again next week. Right, so you
So I
don't
can
have any.
go,
Pardon me?
can go back to
The homework. All right.
Yeah.
I hope I didn't leave anything out. If I left anything out, you can let me know. You can assume something and let me know.
Okay, so thanks.
All right, so you have the homework, so you can try it. I give you the answer there. That's some motivation for you to try it. I know some people don't like doing homework, but I give you the answer so you can actually try it. All right, so I think we can stop here for today, unless you have